Hello everyone. In this video we're going to talk about activation functions in neural networks. So if you remember from my videos on neural networks and the structure of them and layers and so on, we learned that at the end of each layer we pass the output, which is something, the input, which is something like W times A of the previous layer plus B, right? We pass it to a function, and this is the new A, right? So this is like A of M plus 1. It is a function f of the previous layer, something like this, correct? And these W's also belong to layer M plus 1, correct? So this f is the activation function. Now here in this lecture I show it with sigma instead of f, but it doesn't matter, it's just a notation. And we learned a few activation functions, maybe a couple of them. One that we used in Adeline network was the pure linear function, or the identity function, which sigma of x equals x. And this is good when we are doing regression and or function approximation and something. This might be useful, especially in the last layer. And you might say, why don't we use this in all layers? Well, the problem is, if we use this in all layers, then each output of each layer will simply be what? A linear combination of the outputs of the previous layer. And if we keep doing that all the way, then the output of the entire network will be simply a what? A linear combination of the inputs, the p's to the network. So if A of M, A of the last layer at the end of the day, will be some general W vector times the p's, the inputs to the network, plus some b's, where these W's and b's are combinations of the W's and b's of our previous layers. And so what you will have is simply linear regression. And linear regression can only do so much. We learned that it has limitations. If you want to use it for classification, you have problems. You only can separate linearly separable data. And for regression, again, in the last layer, it might be useful, but again, it can only do so much. Most of the time, the functions, the black boxes in the nature that we are trying to approximate from some inputs to some outputs are nonlinear. And if we don't introduce nonlinearity in our systems through these activation functions, there is no other place to do so, because the relation between the weights, biases, and the inputs are completely linear. This is a linear relation. So we have to pass this to some sigma function to create nonlinearity in the system. So that's why we need nonlinear functions to introduce nonlinearity, because most of the stuff in nature are nonlinear. Now, how do we do that? We learned in perceptron networks that were the simplest original networks we use typically for classification. We could use the step function, which basically gives you a positive 1 if the input is positive, and if it's negative, gives you a 0. And it's really good for binary classification. The problem with this is it's not differentiable. This function does not have derivative at this point. And the good thing about it is the output is bounded, okay? So it doesn't grow unbounded. And sometimes you might need that, actually, sometimes not. We'll get to it. But in general, the important thing about it is it's not differentiable. So as we learned in backpropagation, being differentiable is an important thing. Let me look at the formula with you. If you remember, these were the equations, the top two, for updating the weights and the biases. And for them, we needed these sensitivity terms. And the way we got these sensitivity terms were through backpropagation. And if you remember, in them, we needed this f prime, and f prime was the derivative of the activation function. So if we cannot calculate this f prime, we're going to have problems, okay? So we better what? Choose a function that is potentially differentiable, the smooth function. At least the first derivative is important. If you don't have all the other derivatives, maybe not as critical, although it's better be C infinity function, but at least a C1 function is very, very critical. okay, for back propagation. So that's where we chose the sigmoid functions, and I mentioned them to you. So it's a function like this: sigma of x equals 1 over 1 plus exponential negative x. This function goes from at negative infinity is at 0, positive infinity goes to 1, and at 0 is at 0.5. It's a smooth function, beautiful function. It can be used in place of the step functions in perceptrons if we want to do classification. Another good thing about it is it's monotonous. So it's monotonically increasing, so the derivative of this function is always positive. And that's another thing is in this relations, sometimes we really care about this function to be monotonically what? Increasing, because that's the way the neurons in our brain work, which if we give them more stimulus, they will create more output. Now, not necessarily linearly, but clearly, if you connect electrodes or can connect their electric output signal, once you give them a more powerful input stimulus, they're going to create a more powerful output. So it's better that this function is monotonous, okay? Now, this is not centered around 0. Sometimes it's a problem, sometimes not, depending on what we want the output to be. So it's very good, as I said, for binary classification. If the output class is a 0 or a 1, you're good. Sometimes we want the output to be centered around 0. And so that's where there are other functions. One of them is tangent hyperbolic, which goes from negative 1 to 1, and that is e to the x minus e to the negative x over e to the x plus e to the negative x, or sine hyperbolic over cosine hyperbolic, basically. This function, as I said, goes from negative to 1 to 1. It's monotonic, it's differentiable, and the output is bounded. And as I said, let me add that because I mentioned it, this function is differentiable, of course. Okay, the same with the other function that we have, which is the tangent, arctangent function. Let me just add this here before I forget. So the other one is arctangent function, and arctangent function also is differentiable, and it's monotonous. It's also centered around 0, bounded output. The only thing is the output is between negative pi over 2 to pi over 2 instead of negative 1 to 1. So it's very similar to the tangent hyperbolic. Now, the problem you have with the arctangent function, tangent hyperbolic function, or sigmoid function is a problem we call vanishing gradient problem, okay? And that is a serious problem. So let me explain what that one is. Well, the problem comes down to this equation that we used last time. Remember this recursive equation for sensitivities? If you look, every time we want to get the S of the previous layer, we multiply S of the next layer by the weights and multiplied by the F prime. Now, what happens when this F prime term is less than 1? Well, then, as you go back toward previous layers, you go back from the last layer to the one to the last, all the way to the first layer, all of these F primes are multiplied together, okay? So let's say just you have 3 layers, right? Then F prime, right, of layer 1 is multiplied to W of layer 2 times S of layer 2. That becomes S of layer 1. But S of layer 2 itself is what? It is, based on this formula, it's F prime of layer 2 times W of layer 3 times S of layer 3. Now let's say layer 3 is the last layer. So you see here that F prime of layer 1 and F prime of layer 2 are multiplied to get to sensitivity of layer 1. And if you get more and more of these F primes, then the magnitudes of the sensitivities will be small, right? When this F prime is raised to the power n, it's going to be even much smaller than the previous ones. So your terms, this gradient term that you are calculating, multiplying by learning rate, it becomes smaller and smaller. And that's one of the reasons, if you look at my previous video when we did wrote a code for the cost function per epoch versus epoch, you saw that the cost function starts dropping like this, but then after a while it kind of becomes flat like that. So here, if you remember, especially my previous video when I talked about batch update, you saw that it took a ton of epochs for this to barely change 1 or 2%, while only a few iterations, maybe 100 iterations, are reducing the initial cost function by 99%, and then you might need 10 to the 5 to bring that last 1 or 2% down, because this cost function is starting to go down slowly, and especially when the errors are not big, because remember, this cost function depends on the error, and so when the error goes down, then not only the error is small, also these gradients are small, and so you're gonna get a hard time getting the network to improve any further. That's why I said, and that's one of my future videos, that's the time to change this alpha to compensate for the small s terms and bump up alpha, okay? And we're gonna talk about that. But in general, why is it the problem for these three functions? Because these three functions have small derivatives. Let's look at the sigmoid function. So this is the sigmoid function. Remember, it goes between 0 to 1. If you look at the derivative of the sigmoid function, you can plot it in MATLAB. If you do that, you see the maximum value of this function is 0.25. So f prime max is what? 0.25 less than 1. So when you keep using the sigmoid in all of these layers, guess what? As you go back from the last layer to the first layer, you get smaller and smaller s's. So here, s is going what? Down. And so not only along the epochs you get the smaller s's. As I said, when you go back deeper into the network toward the initial layer, s's are getting smaller and smaller. So your last layers are gonna be slow, but as you go back, they're gonna get slower, slower, and when you go toward the initial layers, you're gonna get very, very slow. Okay, so this vanishing gradient is a problem if the derivative of your function becomes less than 1. Okay, and if you know, for sigmoid function, clearly this is less than 1, and like for arctangent, what is it? You know, the derivative of arctangent sigma prime is 1 over 1 plus x squared, right? And again, you know, this guy is always less than 1 as well. What's the derivative of tangent hyperbolic? Well, we can find that as well, right? All you need to do is to get the sigma prime of this function. Well, let me calculate it for you. So it is 1 minus sigma x squared, right? And you know, if you look at this sigma, the value of it is less than 1, so 1 minus sigma squared is also less than 1 for sure, right? And so you see these derivatives are all less than 1, and you get this vanishing derivative, vanishing gradient. So are there functions that do not basically suffer from this problem? Yes. One of them, which is the most common one these days, and everybody's using that, is called the rectified linear or ReLU function. And this is basically like all 0 for negative inputs, and for positive inputs is just x. Or you can write it as max of 0 and x. That's another way to write it. And clearly the derivative here is what? For the positive side is at least 1. Okay, so you don't get vanishing gradient. It is a nonlinear function. Well, what's bad about it? Right off the bat, you can see that at 0, it's not differentiable. Good thing about it, it's monotonous. Good or bad thing about it is it's unbounded output, depending on what you want to use it, but most of the time it could be to your advantage. The data is not centered around zero. Again, some applications do not even require that, and it seems to be working fine. The problem it has is it gives all zero for a huge portion of the inputs which are negative. For all of those negative inputs, this guy will give you zero, so you might call it a dead neuron. Okay, that's another terminology. Dead neuron is when a neuron does not create any output, or at least partially for some inputs it doesn't create any output. Okay, so this is this function, and it has been used very, very widely in lots of different networks, and it seems to be fine actually and working very good in many applications. And before I go forward, I just wanted to tell you one term here. You see here when I showed this network, you see each input is connected to all inputs of the next layer. You see that? Each one of these red dots is connected to all 4 blue dots. Just want to tell you this term. If you ever hear the term fully connected network, I just want you to know that, okay? So this is called a fully connected network, okay? A network that each input is connected to all inputs of the next layer. Okay, so going back now, so this is a good function. It's nonlinear. That's good. It doesn't suffer from the vanishing gradient, but it's not continuous, and it has this dead output, right? No output for some. So can we improve on it? Yes. So here in the following are some functions that have been proposed to compensate for that. One of them is called Softmax function, which is 1 plus exponential of x, the natural log of that. Clearly, when x goes to negative infinity, this is natural log of 1, which goes to 0. When this goes to positive infinity, then this 1 and this 1 is negligible compared to the e to the x, so it's just going to be e to the x, and natural of e to the x is going to be like x. So this function will converge to what? Will converge to y equals x. Or sigma, let's call it sigma. It is going to converge to this ReLU function. Okay, so you see, this is the ReLU function that you have in blue, and this soft plus function is kind of like a smooth approximation to it. So the good thing about it is also monotonous. It does not create bounded output, which is okay in many applications, and it's differentiable. And for negative inputs, it does not create zero. It actually creates positive output. So this is soft plus function. Is that the only one being used? No, there are other ones. Another one is called exponential linear unit, or LU function. You're going to hear lots of LU in because they are all something linear unit. And actually they are not. I mean, like this function, the good thing is this function has no linear. This one does. You'll see this one does, and the next one does. So when they talk about linear unit, a portion of them is at least linear. So what is LU? LU is a multi-criteria function. And for negative inputs, it's an exponential function. For positive inputs, it's just a linear function. So you have one function here, and you have what? You have another function here. Now, if this parameter alpha that is under your control, if you set it to be 1, then this function is differentiable because the derivative at point 0 is going to be 1. Okay, so here at this point, the derivative of left and right will be 1, so the function is differentiable. The good other things is it's monotonous, no bound on the output, and it's not creating any zero output for a bunch of inputs. And again, for alpha of 1, it's what? It's differentiable. For not alpha 1, you're going to have problems. But that is another function, exponential linear. The next function is a simpler modification to the ReLU function. Instead of having 0 output for negatives, they made a negative output for negatives by combining 2 linear functions. So for negative x's, you have alpha times x, right? And for positive, you have x. Now, if this parameter alpha is chosen to be 0.01, 100, then we call it a leaky ReLU function, or LReLU. If this alpha is otherwise other than 0.01, in general, we might call it parametric ReLU function, or P-ReLU function. It is a monotonous. It is a differentiable if alpha again is equal to 1. So the leaky ReLU function is not differentiable. And of course, unbounded output. Okay, so again, typically this slope is what? This slope is much, much less than 1. So it's correct to draw it like this, not like that. Okay, but it could be parametric 1, it could be 1 or even bigger than 1. And the good thing is at least it's monotonous. Now, there is another function that we have, and this function, actually, this is not monotonous. This is called sigmoid linear unit, or SiLU function. What is this? This is like a ratio, and it looks like a what? It looks like the sigmoid function, which is multiplied by a linear function. So we call it sigmoid linear function. It is a differentiable. It's not monotonous. As you can see, it goes down, then goes up. It's unbounded, but of course it's differentiable. That's an advantage. And it does not create non-zero outputs for negatives. The good thing about it is, though, that at least for the negative side, it's bounded. So unbounded on one side, but bounded on the other side. This function is not bounded. This leaky ReLU or parametric ReLU is not bounded. This guy here, right, for negative x's, it goes to negative alpha, as you can see. Okay, so this function on the negative side is bounded. That's good. On the positive side, it's not bounded. The same thing happens to here. This function, when x goes to negative infinity, it goes to 0. On the positive side, of course, it converges to the line function, to the identity function, and this minimum here is at negative 0.278. Okay, there is another non-monotonous function, which is the Gaussian function, e to the negative x squared. Clearly at 0 it's 1, and as x goes to either side, positive, negative, infinity, it goes to 0. It's not monotonous, but it's differentiable. The output is bounded on either side, and one thing it does, it creates the output to look like a what? A Gaussian probability distribution function for you. Okay, so it's not a real one, it's a scaled version, because this max should not be 1. The area under it should be 1 for a valid PDF. But this is what? This is your... or maybe it is actually. The thing is, you have to integrate this, right? You have to integrate this from negative infinity to positive infinity. And you know you cannot do that, so you have to multiply it by itself. I guess it was something related to square root of pi divided by 2 or something. So it's not equal to 1. But this is another function that we have, and this is also used in what we call a group of networks which we call, let me write it for you, is called radial basis networks, which are used for classification, regression, function approximation, and so on. So in radial basis networks, or RB networks, this Gaussian function is used. Okay, two functions here that are used typically in the last layer when you're trying to classify and get one number out of so many numbers. So they are like for the winner, basically. One of them is the max function. Of course, you just out of a bunch of values, you just get the maximum out of them, right? So you want to see this number that my convolution neural networks approximated to be either, it estimated to be either number 0, 1, 2, or anything, like when you're working on the MNIST data, which will work with it in future, right, for classifying numbers. Then you want to pick the output is now which one of these numbers. So I added a picture, and I want to see this picture is which number, handwritten 0, 1, 2, all the way to 9. So I might go ahead and pick one of them and say, hey, look at this number. The outputs are like 0.2, 0.3, 0.5, 0.8, 0.1, 0.2, and I pick 0.8, okay? The problem with this function is, of course, it's not differentiable. The output is not necessarily bounded, okay? So this is not the best way to pick a maximum. Another way that you might do it in a nicer way, smoother way, is this function called Softmax function, where you raise each element in the input, you get the exponential of each element in the input layer and divide it by sum of these exponentials, right? So let's say the input to the last layer has j entries. So you, for each entry, you do the exponential of that divided by sum of the exponentials. And the good thing with this function is differentiable. It's not monotonous like the previous one. And the good thing is the output is bounded between 0 to 1, and it resembles a PDF. So if you add this value for all these j entries, clearly they all have the same denominator. In the numerator, you're adding all these exponentials, so the numerator will be the same as denominator, so you get a 1. So it really creates for you a probability distribution function. So with some probability, this one will say who is the winner. Instead of just picking one as the winner and the rest of them as 0, they are losers, right? We say, hey, this guy is the winner with a chance of 0.8, that guy is the winner with a chance of 0.2, that one is the winner with a chance of 0.3. Okay, so it's kind of like a probabilistic winner instead of just the max function. And it's a smooth function. That's good. Okay, and finally, I want to talk about a function called bionodal root units functions, or BRU functions. These are new in deep learning and neural networks, and these are basically inspired by the brain and the biology. That's why they are called bio. So the thing is, the square root function is used in these function in general, a root function, not a square root, but the function sigma of x equals a square root of x was found to be matching the pattern that they saw in neurons. So they saw the neurons kind of acting like this. Okay, not like that, actually. Something, yeah, that's actually the square root function. That's right, this function, huh? So they found that they are kind of acting like this when they looked at the current frequency relation between inputs and outputs. They found that this is kind of the thing they have in real neurons in our brains. And so they proposed these root functions. As you can see, when r is 2, this is definitely square root function, but r could be any other number. This R is called radix, and it's a shape factor. It's a positive shape factor. And at R, the derivative of the function is what? Maximum. So there are two classes of BRU functions. Class 1, they are called exponential root functions or ERU functions. The second class, they are called odd radical root units or ORU functions. So we have ERU and ORU functions. What do they look like? Well, this is the ERU function. So again, multi-criteria function. For positives, you clearly see it's a root function. For negatives, again, it's an exponential function. So it's exponential root. And this is how it looks like for three different values: 1, 2, and what? And 3. So you see for R of 1, it kind of like that. And then for R of 2 and R of 3, the blue and the black curves. And so you can choose R. The good thing about these two functions are they are both differentiable and monotonous. Okay, and by the way, here is 0 and 0 here. Okay, so these are negatives and these are what? Positive z's. So on the positive side, the root function is used, as you can see. Right, this portion, you see that this part, especially of black and blue, they look like my root function. And for z negative, the exponential is used, which is very similar to here. Okay, so this is this function. And the odd radical root unit or ORU function, it's a sine function of z times a root function. And this is an odd function because if you look at it with respect to 0 and 0, the shape is symmetric. Okay, so it's an odd function, which means f of negative z is negative f of z. Okay, and again, this is for R of 1, R of 2, and R of 3. I got all of these from a paper that was on ResearchGate, and so you can download it. Just search for BRU activation functions on ResearchGate, and you can download the PDF and watch it for yourself. And based on the claims by the people who reviewed ReLU functions versus LU functions versus BRU functions on different types of networks for different tasks, they found that the BRU function is basically more effective in bringing down the loss function. Whether on training or whether on the test data, they found that these BRU functions are better than ReLU or LU functions. So here is an example. You can see some multi-layer perceptron training on NIST data with 4 to 8 hidden layers. And you can see that here the green, which is the BRU function is clearly what? Dropping the cost function a lot faster than the two others. And on the test data, right, you clearly see that it is doing a lot better job, significantly better job on the test data compared to the training data. Okay, and they used it on, I guess, encoders. They used it on convolution neural networks, and in almost all of them, it seems like BRU is outperforming ReLU and LU functions. So these are 14 different functions. There might be other functions, so this is not an exhaustive list, but hopefully I'll give you the sufficient information about the activation functions. Each one has its own application depending on whether you're doing regression, classification, whether you're doing a single class, a multiple class, right? For different tasks, whether you're looking at image recognition and computer vision, whether you're looking at natural language processing, whether you're looking at sequence of data, each one, they have their own application. And as we go through these applications, we'll talk why we choose the activation function for them that we will pick up. Okay, so those individual discussions we'll do later as we go toward each one of them. When I talk about CNN or RNN or AGN or any of them, we'll say why each one of these activation functions should be used in them. Thank you so much for your attention, and I'll see you in the next video.